You have seen this diagram before. It shows that most of the surface of the Earth is either at 800 meters or at around 3.7 kilometers underneath sea level. Less than 10% is higher than 800 meters. Maybe not very much, but still very important. These are the mountains, major features of our planet. Mountains, for instance, are the source of most of the terrestrial sediments we find in sedimentary basins. How do mountains form? In the slide, you see a section across the Alps, a mountain belt where I have also been working for many years. Mountain belts like the Alps are formed by the collision between two lithospheric plates. In our case, these are the European plate in the north and the Adriatic plate in the south. The moho of the European plate deepens towards the south. The moho of the Adriatic plate, on the contrary, deepens towards the north. As a result, the crust underneath the Alps is much thicker than in the surrounding regions. A thick crust is one of the main characteristics of mountain belts. In the mountain belt itself, you see a large number of thrusts, faults which accommodate shortening. Shortening is another characteristic of most mountain belts. We know by now how we can get these mountains. By shortening, the crust becomes thicker, and to reach isostatic equilibrium, the moho deepens and the surface of the Earth moves upward. The hypothesis that topographic creation is associated with shortening is proven by the thrust and by reverse faults in the external parts of the origin. Major shortening takes place at convergent plate boundaries, typically with one plate subducting underneath the other. Rocks of the lower plate are brought towards the convergence zone, indeed an area of strong friction and deformation. Rocks will then be scraped off from the lower plate, piled up, forming an accretionary wedge. A mountain is born. In the slides, you see now a simplified scheme of how a mountain belt forms. At the initial stages of shortening, the orogenic wedge is small and defined by two thrust surfaces with opposite dip. With increasing convergence, the wedge grows because of the mass being transported by the plates and accreted to the origin. Note how the wedge grows but preserves its shape, nicely illustrated by the slopes of the two sides of the origin which do not change their angle. The resultant origin has two very different parts, the frontal and the axial regions. Rocks in the two domains have experienced different paths and will look very different. The two sides we mentioned of the mountain belt are very different. The frontal part is generally wide with gentle slopes. The formation is spread over a large number of shallow dipping thrusts functioning as the fold-bend faults we have seen at an earlier stage. Each thrust accommodates only a limited amount of deformation, it then stops, and its ongoing shortening is accommodated by a new thrust, typically developing in a more external position. As a result, the origin becomes wider. The axial and the back part of the origin, on the contrary, are narrow and have steep slopes. Most of the shortening is accommodated by a few steep faults called back thrusts. Rocks ending up in the frontal regions will never be buried at large depths. They will be deformed when they enter in the collision zone, picked up by thrust, and move back to the surface. As a result, they will not experience high pressures and temperatures and will be broken in fully fragile manner with discrete faults and folds. The axial parts of the mountain belt have very different evolution. Rocks eventually ending the axial part of the mountain have been brought at depths of up to tens of kilometers, and when they get in the neighborhood of the rigid part of the upper plate, can either subduct deep into the mantle or move upward, ending up in the high mountains. Indeed, if you want to search for metamorphic rocks, you need to go to the high mountains. During these paths, the rocks experience deformation at high temperatures and pressures. This result is very different from what we've seen from the low temperature rocks. Having seen all this, you will surely agree that mountains form a very dynamic system. Rocks carried by their convergent plates are accreted to the origin, which starts to grow, and it will grow in a self-similar way as rocks are accreted both in the deep and in the shallow part. Growth of the mountain, however, does not proceed undisturbed. As soon as relief starts being created, rain, wind, and gravity will start their work, first gently, but then becoming increasingly active when the mountains start becoming high and steep. At a certain moment, an equilibrium is reached with the amount of sediments brought into the system being compensated by erosion.